coming today. I had a cup of coffee and an energy drink here, so I'm going to try to keep it around an hour or so, but we will have questions toward the end, any questions you want to ask. And I've got some display items up here that you're all welcome to come have a look at and we can talk about. Some of them I'll refer to as we go through our presentation. So again, thank you very much. I want to start this off. It's dedicated to our crew. Not only the crew that you see here, some of which are no longer with the program, and there's some other staff that we've hired recently, but also the men and women of the Union Pacific. Imagine having an opportunity to work on a steam locomotive as your full-time occupation for a Class 1 railroad. And we're all very proud of that. So we're proud to have them standing behind us. Every department on the railroad in one way or another supports us. Some of them on a very regular basis, and sometimes not so much. But a lot of folks in the headquarters building know us, and we know them, and we're very proud to represent them, and we're proud to operate and maintain the locomotives and the passenger cars. This picture, you might recognize it from the last presentation. This is the day we arrived in Cheyenne. Now, we're not going to talk much about the 4014 directly. This presentation is geared more toward what we've done over the last year and a half with the 844. And we'll go into what we're doing. Now, naturally, the design of the UP, the big Alco steam locomotives, there's a lot of commonality. So a lot of the work that we're doing, the materials we're making, the processes we're developing, all of that, of course, ties right into the 4014. We bought a lot of supplies, a lot of equipment, a lot of material, a lot of stable stock, even some Firebox plate that is directly for the 4014. We're working on tenders, tender wheels, trailer truck wheels, engine truck wheels, all the various things. Very soon we're going to be making the fuel tank for the oil conversion for the 4000. So there's a lot of projects running concurrent with what we're doing. This is also dedicated to my best friend, Ed Gerlitz. Good old Ed. He was responsible for my interest in steam beyond what I had as a childhood interest. And now we're just going to dive right into the 844. In 2013, we discovered a condition in the boiler tubes called over-rolling. And the tubes got rolled. And unfortunately, there wasn't really a good practical way for us to determine the extent of the thinning of that tube wall. So that's a real vexing question for a person in my position, is what do we need to do now? When you've got a small number of tubes leaking, you address them in such a way as to correct that leakage. But when all of the tubes get rolled, that presents a problem, and it could duplicate the scenario that the locomotive endured previous to that.
What do you mean by roll?
The tubes are expanded in a locomotive boiler. A mechanical process known as tube rolling. There's a couple of different processes, but the common steam engine process involves a special rolling tool with a series of small tapered rollers with another tapered mandrel. And that device is installed into the inner diameter, the inside of the tube, and then that mandrel is rotated. And those tapers engage, and as they do, they expand those rolling rollers outward, and they mechanically force the wall of the tube against the ID, the inner diameter of what we call the tube sheet. There's not going to be a test afterwards, but I'll point these out as we go through some of the photographs, and it'll make sense to you. So the process of tube rolling, it's not that scientific. There is a feel to it, like so many things in steam locomotive technology, restoring old farm equipment, hot rods, aircraft. There's a feel to it. There's a lot of old books out there. There's processes. There's official processes that the railroad adopted, and that's what we use. We like technology where we can get our hands on it, where it's applicable, and we've purchased a lot of new equipment, rolling motors and tube rollers. All of those things we've purchased to give us the best possible advantage. Also, a lot of the material that we have in the shop comes from the steam era. And most things mechanical have a limited lifespan. So this is the condition we discovered on the 844. As we began, we were initially just going to take the tubes out of it and simply replace them. So as we started to get into the process of just taking the tubes out of it, I made the announcement to our bosses that we've got a condition that we want to remedy. We're going to need to have the locomotive down for a while, and that's expanded into a full-blown 1472 inspection. It's a federal regulation the locomotives have to go through every 1,472 service days or 15 years. So in the process, this is what's kind of led to that. There's some parts right here, which is what's left over, some sheet metal that was placed underneath the jacket, and this insulation that really became problematic. With the jacket, the way that it was built, it allowed a lot of water to get in there, and that jacketing, which is a fiber blanket, would retain that moisture. And it was just terrible with that pressure vessel, the outside part of the boiler. Because not being painted, now it can rust. And just some more things. These are sand pipes. And again, you know, it's always a tough call when you've got a historic piece of equipment, a legendary locomotive like the UP844, the 3985, the 4014. You just don't start replacing things just that easy. You know, you think about the historical side of it. Some would say that it looks neat having a bunch of dents in it and the old rough look to it. But there comes a time when you need new equipment. This particular sandpipe's seen better days. It's just about worn through. And that's pieces of the cab. You can see more of that insulating material in the jacket, kind of pop riveted together there. And this was one of the worst days I've had. This is the actual steam dome. That's a close-up of the extent of the corrosion. These are the top studs that secure the dome cover. So you can see this heavy corrosion. And what you're looking at is you're looking at metal that's going away. And as that metal goes away, that reduces the thickness of that pressure vessel. So now we have to start doing some pretty serious analysis, taking measurements, running calculations to verify that that metal plating, not just that, but the entire boiler structure, can still withstand the pressure plus the safety factor. And there is the jacket as well. This particular part of the locomotive was problematic because the sand dome is right up here. In the sand pipes, you can see we're connected with a rubber hose connected to the sander. And that rubber hose, unfortunately, deteriorated under the environment of the steam locomotive. So that hose had broken apart and the sand was leaking out and just completely covered that area. So this area right here was just covered with heavy scale, heavy rust. Another really sad discovery is we started taking that insulation off. We lifted the sand dome off, and now we got to completely expose the entire pressure vessel and remove all the piping, remove all the turret valves, remove the top check, remove everything so we can look at every square centimeter of that pressure vessel.
How thick are the walls of the vessel?
It depends on where it's at, but they're quite thick. And this is an area along the combustion chamber, and the locomotive was equipped with a Wilson sludge remover, and it's a centrifuge that operates as you function or you operate the blowdown valves, and it's designed to dissipate a lot of that pressure and not deposit it track side. That's just a process that you have to proceed with when you're operating the steam locomotive. So the design is that water, the effluent, comes out of the boiler and it goes through the centrifuge and releases pressure, but all of the heavy sediment and the moisture will be diverted down trackside. Well, that particular component was just through age and deterioration, didn't really function. It would deposit that water right on that jacket where it would easily find its way through that jacket and then continue to saturate that. So right beneath that location on the combustion chamber, the wrapper sheet, the part of the boiler, and I'll point that out on the next slide, was heavily corroded. And we've got more various things we found, some studs and some bolts welded to the side of the boiler. You can see right above here, that's a remnant of a weld with a bolt welded to the boiler. And that bolt holds something. So that weld, it's not much of a weld, but it's still, you know, it needs to be more secure, and it shouldn't be located adjacent to that cap there. And if I could just ask, we'll have a really in-depth question and answer segment toward the end, if that's okay with everybody. We took the cab off and we found all kinds of things under the cab floor. And yeah, that's a nice snap-on wrench. I wondered where that was. And unfortunately, just through time, this happens with all machines and all equipment. That's a lot of rust, a lot of saturated metal particles, a piece of welding rod and various things. But unfortunately, that's laying against the outside of the boiler underneath the cab floor that you really can't see. And when that gets saturated with water, that just continues to expand that corrosion. Another really unfortunate condition that we discovered was the water glass drains and what we call the injector telltale. They had copper lines that were cut off short and were depositing that water on the back of the boiler. So that was just continuing to saturate that outside of the boiler, and worse yet, that water would go through what we call telltale holes, again I'll point those out, and saturate the inside of the firebox behind the refractory. And that's what led to the next set of discoveries we'll talk about. Some electrical conduits, just a matter of disassembling everything, a lot of piping, the jacket pop riveted together, you know, just not that secure in terms of protecting it. And another thing we discovered was the dreaded A word, asbestos. So we had to perform abatement operations on the 844. So we had to stand down and remove that from the locomotive. That's a special team. We're not doing the work, they are. And here's the cab deck. We're starting to take the locomotive apart, and again, you've got to take everything off of it. Well, on this design of locomotives, just like the Challengers and the 4000s, the cab is actually attached to the back, or what we call the back head, and then it's got these big braces. All that has to come off to expose the back part of the boiler for us to do the analysis we have to do. And here's another decision. As we put something like that back together, how do you do it? When you've got old deteriorated parts, a lot of cases they've been torch cut and holes torched in them, and they may not line up just, you know, when you put it back together. More of the underside of the cab. Inside the cab, you know, bearing in mind that the locomotive has been in service since 1944, this locomotive has not been retired. So what you're seeing is a locomotive that's been putting in really good service over the years. So we're proud to say that it falls to us to make decisions on what parts of it we're going to try to really keep original, but we also have a good opportunity to really fit her out with some really good brand new steel. There's the cab deck. This particular side is right behind the fireman. And if you could see a close-up of it, it's just tremendously rusted. And as rust gets down in these riveted joints, that rust corrodes, and it's quite strong. And as it does, it just separates the metal, and it bulges up, and you can see all these stratified layers of rust, and it just continues, and there's almost no way to stop it. You can't paint, you can paint over it, but you're not going to stop it. Well, there's the new pieces. And in today's era, my foreman, Austin Barker, he's all things mechanical, all things railroad. We're very, very fortunate to have him and our entire staff. And he can take and draw that on CAD, taking our official Union Pacific Historical Society blueprints, and put that right into CAD, and we can send that file to a local steel shop, and they can use their very precise processing equipment to cut out exactly what we have there. So that's about the extent of how we've outsourced this job. We've done everything else. So we can really, really get a lot of good material coming in, and all we have to do is assemble it. So it comes complete with the holes already drilled in it. All we need to do is take the piece of T-iron that I was talking about and drill it and ream it and get it ready for riveting. Take out those bolts, replace it with a hot rivet, and move on. Took us about 2 days to rivet all that together. And here's that piece that I just pointed out here. You can kind of recognize that. So understanding that the original components lasted since it was built, imagine how long this will last. As we put those pieces of metal, we actually installed some tar paper. That's kind of a technique you use on metal tanks, and you warm that up, and the tar melts out of that tar paper, and it saturates the metal surfaces and protects it. And then you paint it, it's riveted together, and it makes it harder for that water to get in there, which will eventually do what water does to steel. There's a piece, this particular piece is behind the elephant ear. And again, how do you put that piece back together? Which hole does the bolt go in? I forgot. It's bent. It's seen many lives of, many years of service. And again, we look at the locomotives as this wonderful piece of equipment that we're really careful with. We operate it just the way it was operated. Back in the days, this was a utilitarian machine. There was 45 of these. And it had a job to do, and that job required that it had to be out on the road making money for the railroad. So the time it had in the shop had to be just get what needed to be done. And the craftsmen and women did a fabulous job maintaining these locomotives, but there's a whole shop full of these locomotives that got to be maintained. There's a new piece right here with some new welded doors behind it. These particular doors access the lubricators. So when we service the locomotive, you climb up behind those elephant ears and you open those little doors, and that's how you refill the lubricators. So we've had problems over the years. The doors didn't work too good. One of them was cut in half, and that would let dirt and everything get down in there, and you'd have to clean it off, and the dirt would get down in the lubricator. So we've kind of made a few little adjustments to make it a little bit easier for us. Now the boiler's coming back together. Things are looking good, but you can see all of the stay bolts, 154 stay bolts on both sides, and all of the rivets down below, all the way around the backside. That was all behind the refractory, the fire brick inside the oil burning firebox. The worst, as I mentioned, the worst part of it was the water glass drains and what we call a telltale for the injector. An injector on a locomotive uses live steam to put water into the boiler. And this particular design, when you're operating a steam locomotive, it's quite loud. And these injectors are the state-of-the-art 1940s. You can't always hear because of the noise of the locomotive when the injector stops working. So it has a feature known as a telltale. It's a small copper line that comes into the cab and deposits into a small little funnel. And then you hear that thing squirting. Sometimes you feel it, you don't hear it. And that's an indication, hey, that injector, what we call broke. It's not delivering water. So the telltale serves a very important function. The drain to that telltale should go down below the level of the boiler and deposit that water where it can just get on the trailing truck or down on the track. And regretfully, it was depositing into the back part of the boiler, and as I said, going through those telltale holes. So as we started to take the firebox apart, we peel back that fire brick, and when we're done talking, you can come up and look at the plate. That's what we discovered. Bearing in mind that that plate has to withstand 300 pounds per square inch. You'll see what I mean when you have a look at it. This is the top part of the boiler. These are where the safety valves go. Some patches, and I apologize for the photograph. It seems much clearer on my screen. There was a roof sheet patch, some really good quality work that was performed ending in 2004. Some more patches. All of these stable caps, every last one of them had to be replaced. A series of other caps that we'll talk about. These two reinforcing plates are what's known as the turret valves. And they take steam out of the boiler and they run all the various accessories, the water pump, the air pump, the dynamo, the blower, the atomizer, the tank heaters, all of the auxiliary steam that's used from the locomotive. So those valves are really important. You have to be able to operate those valves. They're part of an annual inspection. They're part of a daily locomotive inspection. And so it's important that they operate so that you can turn them off if there's an issue. We replaced over 150 studs. Anything from a handrail bracket to something more substantial, such as the turret valve flange studs, the top check studs. I mean, just enormous amount of studs. And to do that requires just diligence. And this is work that, we're not going to be done next week. We put together a really comprehensive timeline. We've got this really wonderful Excel spreadsheet that is itself a work of art, all colorized with dates and times, how many hours employee A worked on this project and so forth. So we can map and timeline our efforts. So we can plan and project and all those important parts of a project. But it truly is, it's humbling when you stop back and look at it. So all those have to be addressed. All of them have to be tapped. Some of them tapped a little bit oversized. And there's a stud, a new one, and the stud that we took out. And to get that stud out, the easiest way is most times to weld a nut to it. Sometimes it'll break off. But the only time they break off is when you can't get to them. If it's out in the middle where you can get to it, you spin it right out with a little bit of heat. And here's some more work. Some more as we were taking the locomotive apart. Here we have a hand-cocked top check. This side is for the injector. The hot water pump, and this side is for the injector. And it also has two shut-off valves there. And there's a bracket here that you can't really see, and there was a broken stud right there. And unfortunately, a piece of angle iron got welded to the side of the boiler in place of the stud. The weld broke and allowed that bracket to move. And as the locomotive is in service, it vibrates, as you can imagine. And that pipe moves through the expansion and contraction, and the hot water and the cold water, and all of those various things. Well, over time, the feet of that bracket had worn down into the barrel of the boiler. That represents another problem. So we have to assess the extent of that wear, the extent of how thin, the thinnest part of it, and fortunately we're 80 thousandths beyond, we're up above that limit. But still something to address. There's sufficient carbon content in this boiler that we have to ask for permission. We have to seek authorization to perform welding by the Federal Railroad Administration. The reason that's in place is just to ensure that we're following a process, the correct process. In this case, we didn't have to weld on it. And there's the new piece. We're going to jump forward just a little bit. A new stud. This is an important one because this holds the handrail. And you can see all the various studs all the way back through there. And you can see this bracket. We TIG welded a shim plate to span over the areas that were weakened, that were eroded. So that wouldn't happen again, and we removed those contact points on that bracket. And we replaced the stud. So we removed this broken stud, we cleaned the area of the boiler that had that welded bracket on there, and replaced that stud. Here's some more studs and more brackets. This is part of the support that holds the front of the cab. Those are 3 brand new studs. Now we're going to go inside the firebox. And I remember having more than one discussion with my foreman, and it kind of goes like this. Well, this is what we have to do. And I get a piece of chalk, and then I take that piece of chalk and I walk over here and I make a line up here and around. All of that has to go away. It all has to be cut out. All of those staples have to be removed. And while we're at it, we're going to replace this. This is the lower part known as the mud ring. Each one of those is a hot rivet, nearly 10 inches long, almost 1 inch in the diameter. So a tremendous amount of work. Well, once we get that plate removed out of there, we discover some other things that we're going to have to address. Because this rebuild, we want this to last 15, 20, 30 years. So we have to address all of the things that we discover. We're not just going to restore the engine for 10 years or we're going to run it a few more times. Everything is done exactly 100%. So when we find something, it's not a matter of, well, I don't think it's that bad. Yeah, I think it's okay. Okay, let's just move on. We deal with it. And sometimes that expands that timeline, that spreadsheet I was talking about. How do you factor in that unknown in that nice Excel spreadsheet I was telling you about? You just kind of, my friend Ed Gerlitz had a saying, you just bow your head and do it. And that's what we do. So this is the mud ring once the plate was removed. And even though the screen has a wave to it, this also had a little bit of waviness to it. For reasons unknown, it had grinder marks in it. Some of the holes with the work was done in a previous life were oversized with a torch or some other device. So we've got to weld that up, and we make a template to the drawing, and we very painstakingly go through and we weld up these variances. The same thing here. This is a condition known as grooving. And this part was not replaced during the last rebuild. The new plate was welded to the old plate. So who knows how old that is? My suspicion is that this is quite old. As the locomotive plate flexes at that point, it undergoes a lot of changes and a lot of stresses. And there's a condition known as grooving that it actually wastes that metal away. Part of it is the erosive action of the water flowing around through there, especially if it's close to one of those blowdown valves. As you open that valve up, that water at 425 degrees, 300 psi is water. As you give it a path to the atmosphere, I mean, it is nearly supersonic in its path out. And it's taking with it all kinds of sediment and debris and other things, and over time it's going to erode to steel. So we've had to clean that up too, and you can't see it, but right in here we've cleaned that up. There was some pretty heavy pits, probably weren't the end of the world, but we've got it apart. So we're going to address that too. So we took and very carefully ground that out, and fortunately that grooving did not extend below that length. This is a big piece of steel known as the mud ring, and this outer sheet is riveted to the other side here. The rivets move through here. So fortunately that grooving was only present from this level up. And that's not the worst of it, unfortunately. There was some more that was a little bit worse. But as you measure it from the outside with an ultrasonic test probe, you can get an idea of what the thickness of that plate is. There's a close-up of the grooving. And now we're going to form this plate. We have in our shop a nice big press brake. And part of the philosophy with having a crew, many of which have never worked on a steam locomotive, is that there's an opportunity to serve an apprenticeship of sorts, to train them and help them develop the skills necessary to keep working on the equipment. So rather than source this out to contractors or people that may provide a workforce, maybe the workforce has a skill set, maybe the workforce has people that they borrow from other places, or in some cases a labor force. Well, along with that, when the job is completed, there goes a lot of knowledge on how to work on this. So my philosophy is we do everything in-house, everything we possibly can. And we're going to do it all, most of it, as much as we can ourselves. We're going to learn how to do it. A lot of it, I've got experience doing it, others have done it, or maybe we've read about it. I mean, how often do you drive big rivets? I mean, who around here really does? There's fewer and fewer people with that heavy type of industrial skill set. So we're going to buy the tooling, we're going to source all the equipment, we're going to do it ourselves. And it's darn fun too. It's a lot of hard work. I'm not, everybody understands, how much hard work it is. So now we're forming this plate, and there it is. So we take this plate, once we got it formed, and rather than drill holes in it once it's there, we take it, we put it on our big mill, and we machine these holes in there. And some may say, oh gosh, you guys are such perfectionists. But when you're fitting something together, the closer tolerances you can make and the more accurate fits you can have for all these welded joints, the better quality job you'll have in the end. Because every one of these surfaces here, this becomes a weld line. We're going to weld that to that piece of plate that we're going to marry up with it. And if we ground it by hand with a grinder and we tried to be as close as we could get, it's not going to be really exact. And so your weld is going to flow through there. And it's just going to continue to be exaggerated. And what you're going to end up with is something that you may not be happy with. Now we've got that plate fit up in there. And once we've welded all that up, that plate fits right in there. We don't have to heat it with a torch. We don't have to get a come along, a chain. We don't have to get a big sledgehammer. And it fits right in there. Now we're going to ream the holes out, make them all the correct size, and we put in what's called a fit bolt. And that bolt holds that together. And we just, every one of those holes is fit with a fit bolt, tightened right down. And when it comes time to rivet it, we warm everything up, we got our forge out, and it takes all of us to rivet, because there's a job for everybody. We've got, one of my Boilermakers is a great farrier. He shoes horses. He's outstanding. So you can imagine the job he's doing. He's running the forge. And we got a couple people on quality control monitoring the temperature of the rivet, because that's important. It can't get beyond a certain point, and you can't drive it if it gets below a certain point. So the quality control aspect of it, we document that. We have everything, all the I's dotted and T's crossed. And it took, in this case, it was funny when we put together a mock-up, everybody wanted to drive a rivet. I want to do it, I want to do it. When we started doing it, nobody wanted to do it really, because it's hard. And it's, it's like, I was a machine gunner in the military, and that's the closest civilian thing I've done to holding an M60 machine gun. And I have to say, an M60 was a lot easier than that 90 gun. So it's fun, so to speak. Now we're going to take these Firebox, the corner pieces, and these represent a real challenge, because they're a tapered cone, and they've got two flat transitions offset from each other. So you just can't lay it out, do some geometry, lay out your bin lines, and put this thing in the brake and press it, because it all kind of comes together as this converging cone. And we bought extra Firebox plate, but we just as soon hit it right the first time. So what we did is we got a piece of steel, and I brought a piece of that over here. It's from the side sheet, and we're gonna do some analysis. Austin is great at trig and calculus, and we do a lot of that because the old books have that. When you go through the Boilermaker layout, and it tells you how to lay this out, there's a lot of geometry in there. Figuring out all the angles, how much does it deflect, how much does it bend. So we go through and get all that figured out. We make a template, and this big frame here is actually a representation of the piece that we're going to put in there. So that top piece is made exactly to the weld line in the top. The bottom piece is exactly the weld line on the bottom, and they're welded together very securely. So now we can take that piece, and we know exactly where to bend it. This particular type of Firebox plate is designed for what we call flanging. It's designed to be formed. So it's a good quality grain structure. It's designed for locomotive fireboxes. It's code material, meaning that it has to have that material test report, and that identification number has to stay with it. Then we make some forming dies, and I brought one of those too. They're quite heavy. We'll draw in CAD these plates, and then we take, when they cut the plates out for us, very accurate, then we'll get the plates back and weld them together, as you see here, and that serves as a press die. You've got a male and a female, and we can use those forming dies in our hydraulic press to now continue to form other pieces opposite what the press brake did. So you can see we broke it this way. We've got all these successive bends. Now we have to curve it. And we do that with the male and female forming die, 75 tons on a 100-ton press, every one of them. And we lay that line out, and we move it through, and you manipulate it by hand, and you make that bend, you form it, and you continue that process. Because not only does it fit like this, at the very bottom it has to bend inward to match up that piece that we've riveted in. Now we're going to weld some lugs on there, because this is about 140 pounds, and we installed a crane inside the Firebox. And this is kind of a conversation we have, you know, where obviously we'd like to be able to get it right the first time, but you've got to make a lot of little adjustments. So we put that crane in there, because you lift that thing one time, you're worn out. So we dolly the thing over there, we craned it in and out of there. I bet you one day we had that thing in and out 15 times. And so it's not demoralizing to everybody. You know, I volunteer to stand in there and run the crane and move it up in there and try to muscle it over in position so the other guys can take a break. We just hand fit it and get it in there. There's the other side. And now we've got the back corners and this door sheet piece here. Well, we've got to drill all these complex holes in that sheet that's got all these breaks in it, plus it's on a radius. How in the world are we going to do that? We drilled one of them by hand, and it took two of us, and it was absolutely exhausting. One hole. So we regrouped, and a lot of the books we've got a lot of neat machines that haven't been used in years in the shop. We found a device, and we cleaned up a lot of these other things, and we made an apparatus that will span between the top and the bottom of the boiler, and then we use that as a foundation to hold our air drill. I'm going to go forward here. Here's that drilling operation. We got that drill off eBay for 25 bucks.
Good deal.
It was a good deal, and it drilled every one of those holes. It's a steam era rolling motor. It's designed for this. We bought those tool adapters and that specialty cutter, you know, just trial and error. You know, just kind of another little side note. Sometimes we'll make tools, we'll have an idea. We had an idea we were going to make this tool that could draw the cutter in from the outside. And one of us could be on the outside operating a handle on a threaded shaft that would draw the end of that cutter. We spent 4 hours making it, and it broke in about 10 seconds. And so, you know, it's demoralizing. But you just regroup, and you've got to find a way to do this. You know, we're not going to get in there with a drill and do it all haphazard. I mean, we're really going to try to make this, because like I said, this is a 30-year rebuild. I've got about 12, 15 years before I can retire. I tell Austin, my foreman, and others on my staff, you know, next time we see this, you're going to be my age. If we do this right, you won't have to be into this kind of work until you're where I'm at in my career. So that kind of motivates us to stick with it. So back to this shot here, we've got all those holes drilled, and you can see they're all in a pattern. And each one of those has a corresponding hole location on the outside. And I'll show you what goes in here next. That's the finished product. That represents a lot of toil and a lot of determination. But the mud ring, we've got a few big 10-inch rivets we've got to put in, but all of this new riveting all the way up to the front of the boiler on both sides. 154 stay bolts here, 154 here, 73, 73, 4 more over here, a grand total of 589 stay bolts. And whenever we do one, we jokingly, somebody on the crew will go, 1. You know, when we install something, we're there working on it for 15 minutes and we'll be done and somebody will go, 1. You gotta have fun. And here's that full penetration welded bolt. My two boiler makers are just outstanding. And the quality of work that they do is evident here. And the other welds that you see. A full penetration weld is just that. That weld goes all the way through the sheet and ties into this bolt. A very strong method of attachment. And at 300 psi, that's what you want. And here's some of our rigid stay bolts. In one day we did 75 of those. And this is on the back door sheet. And they're threaded through, and then they're worked over in this manner here. They're driven over with a special tool that we've duplicated, known as a stay bolt driving tool. The UP has all the drawings. We've simply made those tools exactly to the drawing so we could use their techniques, their methods. Here's that Telltale that I was mentioning to you. But you can see through the outside. And that's how the water was coming from that injector tail and the blowdown water glass drain. It was coming through those holes and saturating all of that metal plating. The locomotive would sit around all winter with a wet firebox. And unfortunately, Mother Nature took its toll and degraded that plate. You can see those beautiful welds right above that. Here's our stay-bolt driving tool, again drawn in CAD. We can send that off to some tool manufacturers that we have working with us. And this is a device known as a porous plug. And it's something that hasn't been used, to my knowledge, in a long time. We found a small supply of these over in the roundhouse, where even still today, we find all kinds of treasures. We find air motors and tools and drills and reamers and all kinds of neat things. They've been sitting over in these steel bins and they're rusty. They haven't been used in probably since the steam era. And we've got one of our guys, he just loves that. It's like his birthday whenever he gets to restore one of these little parts. So what we're doing is we're making this particular device, and this is important because what the porous plug does, I'm going to back up to that. This telltale hole here is your means of determining when the bolt is broken. This side of the bolt is covered with a cap, either welded on, as I'll explain in a minute, or a threaded cap. This in here is at a location that you can visually inspect in most cases, unless it's behind arch brick or a fire brick or grate bearers on other locomotives. So when this bolt is subjected to load, over time it can fatigue and fail. That crack propagates through this telltale hole, and you'll get either a large blow of steam if it's a big crack, or you'll get a small appearance of leak. You know, you're going to get water or steam or scale. That tells you that that bolt is broken. Well, that porous plug serves an important purpose because it sticks in the very end of it, and it doesn't let that sand and soot and dirt and everything get in there and plug that hole up. Because if that hole plugs up, some would think, well, the steam will just blow that gunk right out of there. If it's a small fracture, not really. So that's part of the regulatory process that we still have to follow today. So that porous plug is very important. Now back to the stay bolts here. This is an actual UP drawing of bolts known as the Flannery design. That's the bolts we use. And you can see how these stay bolts are applied. This shows the threaded. This doesn't have the full penetration weld. That's something that was redesigned in its last rebuild. And so far it's working out very good. So instead of this threaded installation here, we have that full penetration weld. But all the different styles of sleeves and caps, this is called an MKS, I'll talk about those. I have one over here, a brand new one that we've made. And I also have these sleeves. All the tools that we've made. It's kind of fun when we get pallet loads of these components that we're having made. We'll buy the coat material and then we'll draw it in CAD, and we'll have a lot of back and forth with the shop that's going to make it for us. Then they'll make us a few test pieces, and if they qualify and we approve them, they'll mass produce a whole bunch of them for us. And they show up in these, big truck shows up and we forklift these things off of there. We're all over there going through them, looking at them. I put a bunch of them on my desk. They're really neat. And there's a KJ flexible stay bolt. We put some layout dye on there just so we were doing an experiment. We wanted to make sure that it fit the way it was supposed to. And there's one of those big boxes, all heat treated, case hardened, ready to go. And that center part, and half of this part on the right side, we've already installed in the locomotive. All three of those compartments were full to the top. And here's some stay bolts. The center one came out of the 844. This one came out of the 4014. This was a piece of stay bolt stock that we had in the shop as part of our inventory. And we did an experiment to determine where the telltale hole was, because you want it to be as close to the center. Well, unfortunately, this one is a little bit off, so we're not going to use that one. We also don't have the paperwork on this, therefore we can't use it unless we go through a process to qualify the material. And because it's not made really the way that we're looking for, it's not really usable for us. We're just going to make new parts. Unfortunately, this one doesn't have a telltale hole. That came out of the 3985. And I've got that one over here. But again, just going through, just doing a little bit of investigative work, looking at things, verifying it's this way or maybe it's not. Here's one of those stay bolt holes, looking through to the inside of the firebox. And here's the new KJ flexible stay bolts all in the back corner. Every one of those is inserted in here, held securely, and then welded on the inside with that full penetration process. Stay bolt sleeve. Some of these sleeves we had to cut out and replace new. As we put the new firebox plate in there, we make a template out of lighter gauge steel that we can form, and we can machine it a lot easier, and it's certainly a lot easier to lift in the locomotive. Then we confirm that all the stay bolt holes are lined up as they should be. And if they're not, we have to make an adjustment somewhere. So we're going off the original blueprint. Well, regretfully, some of these sleeves were a little bit skewed, so the bolt would not fit through and match up to the hole. So we had to cut those out, and again, that's something you're not going to discover until you put the locomotive together. So that was one more thing we had to add to the to-do list. We had to cut those sleeves out, condition the hole, weld them back in, and then proceed on. Here's a drawing of what's known as an FRW sleeve. That's a countersunk design. And now we're going to talk about those turret valves I was talking about up front. Heavily rusted, old, seen many, many years of service. A tribute to the designers of Union Pacific and American Locomotive Company. I mean, this stuff is just rugged. If we built our automobiles the way that these locomotives were built, every one of us would still be driving our first car we ever owned. They were just absolutely a tribute to the engineering. But think about 300 pounds of steam pressure and 425 degrees. You know, that steam is extremely powerful. So we go through and disassemble it. The top is what's known as the stem. And that operates through this threaded part of the bonnet. And this bottom part is the valve. And pitted, really old. You'd probably put it back together and work, but since we're doing it, let's just make new parts. So one of the other things we just add to. And we factor this in when we're gonna, one person is assigned that job, and however long it takes him, that's what it takes him. You know, I'm not hovering on him, hey, come on, no, that's good enough, let's go. You know, it's whatever it takes to get it together and make it right. Because again, this is a 30-year plus rebuild. And there the turret valves are now. All new studs. This is that stem right here. New packing nut, new gland. All new studs, nuts, all new studs here. These are machined, and that operation takes a long time. And that's just how steam locomotives are. You know, if you're looking to just get it together, if you're looking to, come on, this is taking too long, it's probably not going to work out too good for you to work in that shop because it just takes a long time. We got to set that, hold that, and this picture doesn't do it justice. This turret valve is this big. It's huge. So we've got to put this thing, we've got to make a fixture plate, set it up in a mill, and then actually machine that fit up there. And it'll last, probably outlive me.
Original casting?
Yes. Near as we can tell. In the steam era, these parts came on and off engines when they were in service. They'd pull something out of inventory. This component would be rebuilt, put back in the stores. But that's been with the 844, as far as I know, since it was placed in the service it's in 1960. This is an internal part of that. It's a guide. We made those new. This is a washout plug, one of the old ones. And this is the new washout plug. And I brought one of those over there. So we go through, and as you fit those washout plugs, the same thing. We got to make a cutter. We got to make sure the threads are what they need to be. and that cutter fits in those threads, and it cuts that seat that plug mates up against. So it's just a long, arduous process, something that you want a very detail-oriented machinist working on. You don't want them over there with a grinder or a file, you know. You want them to really do good quality work. Because these plugs are not designed to be beat on. But even though they clearly have been, and that's not meant as a joke. I mean, steam locomotives are rugged. This locomotive has been around a long time. Sometimes things leak. And a little tap here and there sometimes is what it takes. But when you've got a plug or a valve or something with steam pressure on it, boy, you're sure taking your life in your hands if you're going to start wailing on it. So it's time for that plug to be placed in the museum. Now we've got some more cutters, and again we go through and you're making all these devices and all these tools, and this tool doesn't work, you've got to modify it, and you just go through a very long process. Little by little, working her together. And we make another cutter, and this is really going to come in handy on the 4014 because the 4014 has mostly the welded style of caps that you can come look at here when we're done, known as an MKS cap, and that's welded on. That welds on all those round protrusions that I was showing you. Well, that's what the big boy has. Well, how are we going to get them off of there? With a torch, a plasma cutter, a hacksaw, a grinder? We made our cutting tool, and we can't take credit for it because we get on the internet and we research the patents on what they made. And this is the actual cutter that they made. How did we find that out? Well, because we got the books. So we do a little bit more research, and we got some pictures of it. Because it's proprietary, they don't really give you good drawings. So with a little bit of work on our smartphones and Google, wouldn't you know it, there's the patent. And it's expired, so let's just make it. And it worked beautifully. And there we are. And we, yeah, that poor guy, for weeks, he's up there addressing every one of those seating surfaces. While we have the caps off, we test the bolts, we check them 6 ways from Sunday to make sure there's no issues. And there was a few of them that we changed out. There were some of the caps that were welded on, unfortunately, and that's not something that is authorized. So we had to carve those things off very diligently to break those free and then address the condition that resulted in it being welded on there so it would seal correctly. And there's the top check valve. The casting in it too, completely rebuilt, all new studs. We had to make a couple of specialty taps there. There it is installed on the locomotive. All new studs on the top, new caps. And these are the studs that hold it on there. And there's a device known as a diverter or a diffusing plate down below here that takes that water as it enters the locomotive and it hits that plate and kind of sprays down into the body of water in the boiler. We needed to address this because just over time, it's hard to say when that had been off of the locomotive the last time, just because of the deteriorated condition of everything. So it's hard to tell some of these things. So when we take it off, we've got to correct that. And that's what that blue is. It's a dice that gives us an indication of how well our machining worked out. And now we're going to get into some of the piping and air brakes. This up in the right corner right here is an air filter. And it's got a filter element in there that needs to be changed as much as you need to change it. But by federal regulation, it's got to be changed every 368 service days. And you've got to look at it on an annual and other inspections. That's the air brake pedestal. And that's where the air brakes mount to. That's the automatic brake valve. Some of these, if you guys watch the internet, I made a little video here just a week or so ago, and I included some of these videos in that video update that we produced. That's the underside of that. And again, it's required that these have to be gone through. It's an air brake component. It's regulated by the FRA. You've got to go through a specific work scope. Doesn't matter if it's a steam locomotive. Air brakes are air brakes. You got to work on them. So we went through, got it all cleaned up. We were very fortunate that Westinghouse Air Brake, when I reached out to them some years back, I had a contact there, and they had been following the Big Boy project. And this individual is, much to my surprise, quite an enthusiast. And so we got the dialogue going, and they were able to get a hold of the rubber plant. And for the first time in my memory, they said, yeah, we have these old molds. Let me see if we can make them for you. Because previously, when we'd asked about gaskets, oh, that's obsolete. No, we can't do it. So I just kind of had figured out, we're just going to have to figure out how to make these gaskets. They were able to make a lot of the old number 8 gaskets for us. So that was really neat. So we have the actual Westinghouse brand new 1940s gaskets. Yeah, from Wabtec. Yeah. So our hats off to them. And again, going through this is a detailed job where you really want somebody who's patient, going to go through and really painstakingly clean everything up. Almost like taking apart a fine watch. Inside there's internal bushings. This represents one of the last locomotive air brakes utilizing the rotary type valve. The newer systems, not long after this system was in use, employs a much more, a different, more modern technology. Well, these rotary devices, of course, they wear, so we took the bushings out, put new bushings in. So there again, I mean, this air brake system, and it's the same air brake we have in the 3985 and the 4014. So we're going to rebuild all that the same way. We already have all our own tooling and gaskets. So coming together, here's some of those brand new Westinghouse gaskets right there with the Westinghouse name on it. Box full of little wasp traps. This is a valve inside what's known as a distributing valve. And that is a very important part of the system. It didn't look like that when we took it apart. And there it is inside the distributing valve. And back here you can see we've got that internal area there all cleaned up with a special insulating varnish. There's a feed valve. That controls the pressure to the brake pipe. Very important. It's a high capacity regulating valve. And that's what it looks like when she's all ready to go back together. That's one of the gaskets that clearly wasn't serving its purpose. But there again, a tribute to the locomotive design. It's amazing that stuff still works. You know, and it's designed that way. When you read the air brake books, and Westinghouse put some very comprehensive booklets out to train, mainly geared toward engineers, the operating aspects, but there's a lot of good mechanical information in there. It wasn't the rebuild manual, but it explained how those things work. Here's that filter I was talking about. I don't think they've made that filter for a long time.
It's like vacuum cleaner.
And there's the new version. Yeah, we put a K&N filter in there. Those hot rod guys in here. That's the cab signals. Very, very important part of the locomotive. And here's the rebuilt version. And we'll take that, and that will be the same device that we have on the Big Boy. We've got all our parts, all the magnet valves, all the check valves, everything. We've got duplicates of everything, probably times 2 or 3. We've got plenty of spare parts. We're going to rebuild one system, we're going to make 2 or 3 others. Brake application valve, all rebuilt, all new fittings. This is the throttle. Now some people are probably going to be upset when I tell you this, but what are you going to do? Are you ready for this? Okay, I nickel plated the throttle. As we were taking this apart, I mean I have to say I'm just humbled that all of us have the opportunity to work on the locomotive. I've run this locomotive since 2005. And I've run it thousands and thousands of miles all over the place. And what a grand machine it is. So that throttle represents a lot to all of us. And it's such a magnificent machine. You know, to me, to a lot of us, this is the railroad equivalent of Air Force One. This is the heritage of our railroad, and I like to say our nation. You know, it's a very important piece of equipment that we're responsible for. So we give it its due respect and attention, and okay, I nickel plated the throttle. And I also nickel plated the reverse.
He's a man.
Anything? Recast?
The question was if we've had to cast anything, and we have. Yeah, we've used some foundries. They're steam bronze. In this case, we've got other parts that we've made. We've cast to those parts. We make it just the way that they're made. They're designed to be made. Sometimes we have to do a little bit of reverse engineering. We'll take, and oftentimes when we're not sure, especially if it's code material or if it's a component that has to be made out of code material, we'll take a sample of that and we'll send it off and we'll have it analyzed. They'll put it through a spectrograph and they'll give us the chemical composition and a certified report so we can certify what it is. And from that we know what material to make it out of.
Are you going to take any parts from the 4004 for the 4001-4 rebuild?
The question was, are we going to take any parts from the 4004 in Cheyenne? The answer is yes. And that was, it wasn't a big factor in restoring a 4000, but it certainly was something that you had to consider, that we only have one more 3900 class big Challenger, and that's the 3977. And we don't have many FEF3s or other locomotives that we can use for the 844. So, but we do have 7 other examples of 4000 class locomotives. And so we do have a source of parts. They're not brand new, but it is a source of parts for us. If it's a component such as this actually came off the 838, one of the locomotives we have in Cheyenne. The 4005, the 4004, all the 4000s have lots of these. And so that's something we're not going to have to duplicate, because we have opportunities to reach out to the owner of those locomotives and see if we can't work something out. Yes, sir.
Given the fact that you're advancing towards retirement, are you going to get this done before you retire? And what's the time frames for any of these things, knowing how careful you are?
That's a good question.
To come to fruition.
That's a good question. We do want to have the 844 done this year. That's what we're pushing for. And the 4014, we're pushing for 2019. And as I mentioned, we've got a lot of the materials that we've bought. We've got timelines, and we've got a lot of concurrent activity going on. But there is 8 of us. So, you know, but we're very confident that we can progress this. Yes, sir.
Any chance the 844 is going to be done by Cheyenne Frontier Days?
That's another good question, and that's what we're shooting for.
This
So
year.
bear in mind, we've got to do some break-ins, and this is one of these things where, you know, we wanted to have it 2 years ago. I wanted to have it last year. So you don't think my name's mud with a few people, possibly, or I'm not on somebody's dartboard. But the reality of it is that we have conditions that we've got to address. And, you know, they understand that. This is the heritage of our fleet. It's the pride of our fleet, but it has to be done correctly. Yes, sir.
You were saying that the replacement lagging tended to saturate with water. Did its predecessor, which I assume was asbestos, was that equally likely to saturate or a little less so?
Well, I can't really speak to that, because although I've seen asbestos on locomotives, and yes, it does retain water, it's just the nature of the cycles of maintenance that locomotives undergo and the service that they're under. And again, you know, the other factor is the longevity. I mean, these locomotives were projected to live into the 1960s. They were able to dieselize by 1959. There were plans before World War II. They were going to be dieselized much sooner. So as these locomotives were on the drawing board and being produced, they had no idea that it was going to live into its 70s. So that is another factor there. The insulation that we'll use is a very common insulation used on most steam locomotives, and it just comes in a block form. You know, it's not waterproof. It does get wet and it does break down.
Yeah.
But that's why it's important to have a couple of things. A good secure jacket, because we do wash it and it does rain. So the other part of it is when the locomotive is in service, the external part of that boiler is very hot, considering your steam pressure is at 425 degrees, your temperature. But when you put the locomotive away, that is the most important part of the locomotive's life, because water does what it does. And there's so many little intricate parts of a boiler, even though the thing looks massive and huge. There's so many little bits and pieces of it, all those threaded, thousands and thousands of threaded connections. Every one of those tube installation points, all of that can corrode, and it will corrode. So what you have to do is you've got to reduce that. The atmospheric oxygen continues to drive that corrosive process. If there's water present, the atmospheric oxygen oxygenates that and sustains that level of corrosion. You've got to stop it. What we do is we heat it. We got these big giant heaters in there, and we smoke that thing. We get that firebox absolutely smoking hot.
Dry everything out.
And when we wash it, we don't go home until it's hot and dry. And we make sure we've got lights that indicate that we've got this thing on. You go by that firebox and it's hot. We got the washout plugs out. I mean, we're smoking it. Take the superheaters out. I mean, all of it. It's a lot of work. That's why you don't see a lot of steam engines running, because they are a lot of work.
Also, is 844 ever going to get its Mars light back?
You know, I was kind of funny. I've read. I don't read a lot of stuff on the internet because it's so true. But the Mars light kind of came about in a unique way. We were in Council Bluffs and we were looking, and there was some studs that hold it to the smoke box door, and several of them were broken. And that Mars light's big and heavy.
Yeah.
And so we went in and just took it off. And I thought about taking the elephant ears off and everything else, but we just don't have a lot of time for that. And I like the elephant ears. But yeah, we'll put the Mars light back on. But we decided to, what the heck, we wanted to see how long it would take for somebody to notice. And
There was a true Mars light.
Yes, yeah, a pile gyrolite. Yeah.
Are you close to a hydro test?
Pardon me?
Are you close to doing a hydro test?
Yes, yes we are. We'll be stuffing tubes in it starting tomorrow. So we've painted the inside of the barrel of the boiler. I've got some other photographs that I didn't include because it gets real long. But we cleaned the inside of the barrel of the boiler. We had to shorten several boiler braces. You know, that's the only time you can do that level of work, and when the tubes are out of it. So there were some tube sheet braces that were a little loose, and as required by the way it has to be, we needed to tighten those up. We did that months ago. But just one little thing at a time, and just kind of progressing yourself toward getting the locomotive together. Yes, sir.
What kind of whistles you got on each locomotive?
They're all hand-cocked 3 chimes, and ironically, that my friend Ed Gerlitz that I mentioned at the beginning of the presentation, he had a vast collection of whistles, headlights, and all kinds of railroad stuff. And in his collection, he acquired several hand-cocked whistles. But to answer your question, it's a hand-cock. The whistle on the 844 is actually off of a 4000. Ed, before we announced the 4014 project, before it was even in the works, I was trying to nail him down on which 4000 it came off of. And he would just say, oh, it's so long ago, why do you always do this to me? And so we've got the 841, we've got the 4014, plus the whistle that was on the 4014 when it left in 1961, but who knows what whistle that really came off of. But the whistle that we have on the 844 comes from the Ed Gerlitz collection, and as you and I can attest, it is loud. The one that was on it previously was just steam cut, and it kind of had a raspy sound to it, and we wanted to work on it a little bit, but we just didn't have time to remachine it, so we just simply replaced it with that whistle that was currently on it, and it'll stay on it.
Yeah.
We might switch it around. The 3985 has a whistle that's been on it for years. I love that whistle. It has a very prominent low tone,
Yeah.
and I like a single note whistle personally, if we want to talk about whistles. If I could admit to being a guy that likes trains. But that 3985 whistle is, it has a really nice sound and a lot of fond memories. I've operated that locomotive a lot, fired it tons. It's a tremendous locomotive.
That one's on hold for now then.
It is.
Indefinite or likely eventually?
One never knows. You know, I certainly don't like to use the word indefinite or permanent or anything like that, because if you were in a position such as myself and you had superpower locomotives, would you run them? Would you restore them? And, you know, I think everybody would agree, yes, certainly. It's a tremendous representation of that locomotive. It has a great story behind it, how it was restored and brought back to service. Great people got together to restore it. For many years, it served as an ambassador, and a great one. So it's a fine locomotive. We look forward to doing everything that you see here to the 4014 and the 3985.
Yeah.
Imagine having a roundhouse with 3 of those things steamed up.
I recall reading the Trains magazine probably 30 years ago, they're talking about $44.99, an editorial about keeping it maintained without any deferred maintenance.
Yeah.
And they were talking at that time about $1,000 an hour of running time.
Yeah, I've pretty well figured out what it costs to run those things, but I certainly don't like to talk about it. You know, I mean, realistically, why would you want to run a steam locomotive? Because they're fascinating, and it's a great ambassador. It's a great tool. Yeah, we can talk about it from that standpoint, but realistically, it's a steam locomotive running today. You don't need to be a train buff or a rail fan photographer. They are just really neat machines. They're absolutely one of the best ways to reach out to people. And they don't even realize you're reaching out to them. I mean, the locomotive rolls into town. The thing is so enormous, it's alive. I mean, it feels like it is. It's just the magnitude of a steam locomotive, the fact that everything on it is hot. It's designed to be hot. It's not breaking down or wearing out. But it's just a really neat thing. And the whistle and the sound it makes, the exhaust, it just captivates people.
I thought the whistle was kind of sick on the 14. Was that low pressure, low air pressure?
That's because a diesel was making it work. It was protesting. we have this is a little bit of a story, and I've told it before. When we wanted to blow the whistle, but we only wanted to blow it the moment that we came out on the American Railroad Network. So it took a lot of discipline for us not to toot that thing every now and then as we were coming across the parking lot. But we put a big air reservoir off of an SD70 locomotive, put it on the tender, and we plumbed it all up, and we ran that main reservoir air pressure from that 4884 diesel behind us. And as soon as we came out on the main line, I had it all worked out in advance that Paul Gershio, he was one of the members of the museum. It was up to them who blew it, but one of their museum staff was to blow the whistle. And they were a bit timid at it, and I told them to do it again. I was on the radio, and just before we started to move, the whistle wasn't blowing, and I reminded them. And then I realized I was standing right next to it. I was on the front, and before I could put my hands up, that whistle blew. And I believe that's it.